you have z is equal to f of xy. This is what you have. You can write this as dz equals to fx dx plus fy dy. This is what you will write. Then you again differentiate this. So what you get is d2z equals to you should be writing it like this. Just wait. So what you should be writing is that it should be del of dz by del of x dx plus del of dz by del of y dy. Okay, this is the second order differential. So let us try to differentiate dz with respect to dx first. So what you will get is I am differentiating this dz for this term. Okay, so what I'm going to get, differentiating this with respect to x again. So what you will get is fxx dx, then fxy dy plus fy del of dy by del x. Okay, this is this term del of dz by dx into dx plus, now differentiating this dz with respect to y, now finding out for this term, which will be f of xy dx plus f of yy dy plus f of y del of dy by del of y dy. Okay, so simplifying this further, what you're going to get is fxx dx square plus what you will get is, let me not write this 2 here, which is f of xy dx dy. This is what you will have, plus fy del of dy by del of x dx. You will have f of xy dx dy, f of yy dy square, f of y del of dy by del of y into dy. This you will have. Now taking all the like term together, so what you will have is f of xx dx square plus 2 f of xy dx dy, f of yy dy square plus, you take f of y common, and what you will have is del of dy by del of x dx plus del of dy by del of y into dy. This is what you will have. Okay, so you can again sort of simplify this. So what you will have eventually is what you will have eventually is f of xx dx square plus 2fxy dx dy plus f of yy dy square plus f of y d of y. This is what you will have from here. And this is actually the second derivative of y. So you can write this as f of xx dx square plus 2 f of xy dx dy plus f of yy dy square plus f of y d2y. This is what you will have. Okay. Now, what you will have is this is d2z. Okay, you have to remember this. And you have a constraint also. Your constraint is gxy equal to 0. This is what the constraint is. Again, taking the differential, so we will have dg equals to gx dx plus gy dy. And you can take up the same procedure as we have taken up above, and you will have the exactly same kind of the expression here also for d2g, which will be gxx dx square. The same procedure which we have followed for f of xy, you can get here also. 2gxy dx dy plus gyy dy square plus gy d2y. This is what you will have. Okay. Now from this you can get the value for d2y. From this equation you can get the value for d2y. So what you will have is d2y is equal to, okay, what you will have to do is basically you'll have to put d2g equals to 0, and what you will have is gxx dx square plus 2gxy dx dy plus gyy dy square, this minus sign here for everything. This is some messy calculus. Okay, this is the value for d2y. Now what we have to do is that we have to put this d2y here into this part. Okay, so this is the way what we'll do here is, and in case if you substitute this d2y which you have calculated into the part here, so what you will have is, let me write with a different ink altogether. So in place of d2y, what I want we have to write is this thing. I'm not cutting it. Okay, so just wait. I'm just copying it. Okay, so this is what you will have. Okay, this is the entire expression which you will have for, this is the entire expression which you will have now. Okay, once you have substituted what you have got from d2y, sorry, from the last from d2g, and you have substituted it here, and calculating it further, you can actually write, what you can do is, let me just copy it down again for you guys. Okay, so let me just copy till here. and let me put it here. And let me again copy this. Let me put it here. Okay, this is the entire expression which you have for d2z. Now what you have to do is, again, you will have to take all the like terms together. So in case if you will take all the like terms together, what you will have eventually is, that is, you will have fxx minus fy gy gxx dx square plus 2 fxy minus fy by gy gxy. I've just taken all the like terms together, so it is dx dy plus fyy minus fy by gy into gyy dy square. Okay, so you will have this term. While in case if you look at what you can also have is, from the above equations, if you remember, this is what we have calculated. Fy is equal to minus lambda gy. So you can substitute it here. So wherever fy is, you can write minus lambda gy. So remember, your fy is equal to minus lambda gy, or for that matter, lambda is equal to minus fy by gy. Okay, so wherever fy by gy is, you will be putting lambda. So what you will have eventually now is fxx minus lambda gxx dx square plus 2 fxy, it should not be minus, it should be plus lambda gxy dx dy plus fyy plus lambda gyy dy2. Now, and this is, all of this is d2z. Okay, so what you can probably write is that in case if you have the Lagrangean function, okay, supposedly in case if you have the Lagrangean function fxy plus lambda gxy, this was the Lagrangean function. Now tell me one thing, what is Lx? Lx is del L by del x, which is fx plus lambda gx. Fine. What is Lxx? Which is fxx plus lambda gxx. And this is the first term which you have here. So let me write it here, which is Lxx, okay, into dx2. Now, again, what is Ly? Ly is fy plus lambda gy. What is Lyy? Which is fyy plus lambda gyy, which is nothing but this last term, which is Lyy dy square. And then what is, you have calculated Lx, so you can calculate Lxy. You have calculated Lx, you can calculate Lxy, which is fxy plus lambda gxy. I'm so sorry, this is not x comma gxy, this is gxy. Well, that is nothing but this middle term, so which you have plus 2 lxy dx dy. This is what you will have. So basically you have reduced d2z into lxx dx2 plus 2 lxy dx dy plus lyy dy2. Now in case if d2z is less than 0, the point which you will get, the critical point which you will get, that point will be the point of maxima. And in case if d2z is greater than 0, then the critical point which you will get will be the point of minima. Okay, now what you have to do is that you will have to get the determinant. Okay, you'll have to form the bordered Hessian, which you have already talked about in one of our earlier recording. So you'll form the bordered Hessian. Okay, and in case if the sign of the determinant is going to be positive, that will be the point of minima. In case if the sign of the determinant is negative, then that will be the point of maxima. So bordered Hessian will look like 0, gx, gy, gx, gy, lxx, lxy, lxy, lxx. We've already talked about this in one of our earlier recording. And okay, let me just put it properly. So this is the bordered Hessian matrix. So it is bordered by the first order partial derivatives of the constraint function, and then you have the second order derivatives of this Lagrangian function. So this is the bordered Hessian which you have. Now you will form the determinant of this bordered Hessian. Okay, you'll form the determinant of this bordered Hessian. Now in case if this is going to come out to be positive, that will be the point of minima, and in case if that comes out to be negative, that will be the point of maxima. Okay, so this we have already talked about. So this was the entire proof for the Lagrangian function. That is, how do you get the first order conditions and second order conditions in the Lagrangian function? Okay, thanks.